This example considers the cooling of a gas turbine vane and is approximated as a tube of 3 millimeters of diameter and 75 millimeters of length. So this is a schematic of the vane, which is simplified as a tube. So the operating temperature of the vane is 650 Celsius, and the air enters at 427 Celsius, and the flow rate is given as 18 kilograms per hour. The question is to calculate the temperature of the air at the outlet and the heat transfer removed to the blade. So first of all, to analyze the problem, we have to find out the material properties for the air that is passing through. For that, we have to take the average of the mean temperature of the inlet and the outlet. However, the outlet temperature is unknown, so we have to assume some temperature. So the temperature will be something in between 427 and 650. So it is right to assume a value of 600. We can always go back after we finish the exercise and do a second iteration. So for this temperature, the resulting average is 513 Celsius, which is equivalent to 786 Kelvin. So we go to table A4 from the book and compute the properties. So the most important are going to be mu, which is equal to 3.67 10 to the minus 5 seconds per square meter, and Prandtl, which is equal to 0.7. So the initial point is to compute the Reynolds and the length for fully developed hydraulically. Reynolds definition is rho multiplied by the velocity multiplied by the diameter and divided by mu. Different form of Reynolds in a pipe can be computed as 4 times the mass flow rate divided by pi, the diameter, and the viscosity. As we already have the mass flow rate, so this is 5 multiplied by 0.18 kilograms per hour, and we have to transform it into kilograms per second, so we have to divide by 3,600 and divided by pi, the diameter, which is 0.003 millimeters, and the viscosity, which is 3.67 10 to the negative 5 in the proper unit. If we do the operation, so we obtain a value for Reynolds equal to 578, which is a laminar value. So given that it's laminar, we have to use the corresponding equation for the distance to fully developed flow. So X for fully developed hydraulically is equal to Reynolds multiplied by the diameter and divided by 20. So this is for laminar, and it will give us a value of 0.088 meters. So if we compare with the 75 millimeters length, we notice that the flow is in the entry region. Also, we know that Prandtl is equal to 0.7. So Prandtl equal to 0.7. So with these two, we get to the conclusion that we have a combined entry region. Now that we know that we are in the entry region, we need to compute the nozzle number using the corresponding correlation. We compute the nozzle number using the entry region diagram, which is in terms of the Graetz number. Is D multiplied by Reynolds multiplied by Prandtl and divided by L. And replacing the corresponding values, we obtain 16.57, and the value that we need in the table is 1 over grad, which is equal to 0.060. Now we have to go with this value to the graph. So we have 0.060, which I already highlighted in this point, and we have to move to the plot corresponding to 0.7 Prandtl, which is approximately the top one, and with that one we move to the left and we obtain that nozzle is approximately equal to 5. From the graph, nozzle average is equal to 5, and therefore by the definition of nozzle, which is h bar multiplied by d and divided by k, we can solve for h and obtain that is equal to 93.5 watts per square meter Kelvin. With that value for h, we can compute the temperature at the outlet. Remember that the equation is delta T at the outlet divided delta T at the inlet is equal to e to the minus PLH divided by the mass flow rate and Cp. From this equation, we can solve for delta T at the outlet, which is delta T at the inlet multiplied by e to the minus PL mass H divided by the mass flow rate Cp. And so by replacing the corresponding values, we have that T at the outlet is equal to 583 Celsius. The next question is to compute the heat removed from the vane. That can be accomplished using the equation for the heat of convection, which is equal to H multiplied by the area, which in this case is P multiplied by L and multiplied by delta T log mean. So we need to compute first the delta T log mean. So let's initially plot the temperature. So we have, so this is x equal to 0, this is x equal to L. So this is the temperature of the surface, which is constant, and the temperature of the air in the vane has this shape. So the initial temperature given by the problem is 427 Celsius, and the final temperature that we just compute is 583 Celsius, while the temperature on the surface is 583. So we have two distances. So the first one is this, and this is called delta T at the inlet, and this is delta T at the outlet. Now delta T log mean is equal to delta T0 minus delta T at the inlet divided by the natural log of delta T0 divided by delta Ti. By replacing the values, we will obtain that delta T log mean is equal to a value of 129C. By replacing this value in the equation for the heat transfer rate, we will obtain that Q is equal to 8.55 watts. Well, this is not the only way of computing the heat transfer rate. Alternatively, we can compute Q as the mass flow rate multiplied by the Cp and multiplied by the mean temperature at the outlet minus the mean temperature at the inlet, and we will obtain the same value.